All right, today we're tackling one of the biggest cold cases in all of physics, the hunt for quantum gravity. Think of this whole thing as a detective story. Our suspect? It's invisible, and the only evidence it leaves behind is a footprint that's pretty much impossible to find. So let's start the investigation.
So that really is the million-dollar question for physicists, right? I mean, gravity is literally everywhere, but its quantum side is so elusive, it's like trying to take a picture of a ghost. So how do you even begin to set a trap for a fundamental force of the universe? Well, the very first step is to understand our suspect. So let's dive into what makes this case feel so impossible from the get-go. Our suspect is this hypothetical particle called a graviton. It's the smallest possible piece of gravity itself. And trying to catch one? Yeah, it's absurdly difficult, and the reason why is actually kind of simple. When you stack it up against things like electromagnetism or the nuclear forces, gravity is barely a whisper. It's just so incredibly weak. And that weakness means that any quantum footprint it leaves behind is going to be incredibly faint. So the first job for our detectives, the physicists, is to figure out the odds of even seeing a clue in the first place. And this right here is the absolute first move. See, scientists can't see the graviton itself. What they're hoping for is that it'll interact with a super strong magnetic field and transform into something they can see, a particle of light, a photon. But, calculating the actual odds of this happening, well, that's where things get really, really tough.
So what it all boils down to is this huge imbalance. On one side of the equation, you've got things we control, like how strong our magnetic field is. But on the other side, you're up against these cosmic behemoths, these unchangeable constants, like the speed of light, raised to the fourth power. And that just creates an outcome that's so tiny, it's almost zero.
And wow, here is the number you get. This is the actual probability that one little unit of gravity will flip into a flash of light we can see. It's a number so small, it practically breaks your brain just looking at it. To try and put that into perspective for you,
And that just perfectly sums up the challenge, doesn't it? You're on the hunt for a clue that is less likely to show up than finding a single, specific, marked atom in the middle of all the planets, all the moons, all the asteroids, and the sun itself. So with odds that low, how on earth could you ever expect to find anything?
all right, so that brings us to the next phase of our investigation. Just knowing the odds isn't enough, right? You have to turn that tiny probability into a signal you can actually predict. You've got to set a trap and calculate exactly what you expect to find. Okay, so the way they do this is pretty cool, and it breaks down into three main steps. First, the theorists predict how many of these gravity units should be zipping through the detector every single second, and it's a massive number. Then you multiply that huge number by that microscopic probability we just stared at. And finally, you have to account for your hardware's own little quirks, its efficiency. And when you put all of that together, what you get is the golden clue. It's not just a probability anymore, it's a target. It's the precise number of light flashes the experiment should see if quantum gravity theory is right. This is the fingerprint. This is what we're hunting for in all that data. Okay, so we have our target. Now we've got to find it. And this is where the software really takes over. It acts like a digital forensics lab, and its job is to be a digital dragnet, combing through millions and millions of false leads to find the real piece of evidence.
You have to understand the raw data you get from a detector, it's not clean at all. It's a total storm of information. The hardware itself creates false alarms just from heat or random little electrical glitches. They call these dark counts, and they create this constant background static that could easily drown out the tiny real signal we're looking for. So the software's first job is to cut through all that noise.
So the first filter they use is actually pretty brilliant. The software looks for accomplices. See, a random glitch, that's probably just going to hit one lonely detector all by itself. But a real physical event, like our graviton turning into a photon, boom, it's going to scatter and trigger a whole cluster of detectors right next to each other at the exact same instant. We're talking within a trillionth of a second. The software just automatically deletes the lonely flashes and only keeps these clustered events. Okay, next up, the software gets even smarter and learns to ignore the room's constant, predictable background hum. Over time, it calculates the average rate of all that background noise. That's the middle bar there. Then it just digitally subtracts it from everything it recorded. And what's left behind? That tiny little bar at the end. That is our isolated signal. That's how we go from a total mess of data to just the events that really truly stand out. So you see a spike. Is that it? Case closed? Well, not quite. To prove it's a real discovery, physicists use a standard called 5 sigma. This is the final mathematical proof. It's a calculation that basically proves your signal is so much stronger than all the random noise that there's less than a 1 in a million chance it was just a fluke. If you hit 5 sigma, congratulations, you found something real.
But even with all these amazing filters, there's one last tricky problem. What if a random bit of noise is a perfect imposter? For that, the team brings in the specialist, the most advanced detective on the team, and artificial intelligence.
And this really is the final, toughest hurdle. Sometimes a random cluster of glitches can perfectly mimic the signature of a real event. It can fool all the mathematical filters and look just like a genuine discovery. So how do you catch a fake that looks absolutely identical to the real thing? Well, you do it by training an AI to be the ultimate detective. You basically show it millions and millions of examples. Here's what a perfect simulated quantum gravity signal looks like. Here's what a nasty hardware glitch looks like. And here's some random thermal noise. Over time, it gets incredibly good at spotting the subtle, almost microscopic fingerprint that tells a true event apart from a really convincing fake. So this AI isn't just, counting flashes. It's doing something much more sophisticated. It's analyzing the very character of the signal, its shape, its timing, its rhythm. It's basically our final expert witness on the stand, confirming in real time that what we're seeing isn't just a statistical blip, but a true physical event. And with that, we've arrived at the end of our investigation. After all the filtering, all the math, and the AI interrogation, we finally get to the verdict. How do we know for sure that we've actually closed the case? This right here, this is the moment of discovery. When a signal makes it through all those filters, smashes that 5 sigma statistical threshold, and gets the final stamp of approval from the trained AI, that's it. That's when scientists can say with real confidence that they have captured the quantum footprint of gravity. I mean, it is the culmination of this whole incredible journey. From a probability that's almost zero to a verified signal glowing on a computer screen. The case is officially closed. The invisible suspect has been caught. And really, this is where it gets so exciting. Because finding the footprint is just step 1. Learning how to actually detect the quantum nature of gravity could unlock some of the deepest secrets in the cosmos, from what's happening inside a black hole to the very first moments of the Big Bang. The investigation might be over, but the real exploration, that's just getting started.